So for section 10.2, this is going to be a review of the polar coordinate system that was discussed back in your pre-calc honors days. So when we talk about the polar coordinate system, again, you're talking about a fixed point, which in the polar coordinate system, we do not use the phrase origin, but we use the pole. We talk about the pole, remember, as the origin of what we think of in rectangular. So that is what we call the pole. And a ray extending from O is called the polar axis. And the polar axis is what you think of in rectangular as your x-axis, your horizontal axis. Just different vocab. To locate a point P in polar, again, we're drawing a line segment from the pole to that particular point. A point in polar, remember, is expressed in terms of r comma theta. So r is the length of the radius, that's the number of units away from the pole. Theta is the angle measurement that's being formed with the polar axis. So some conversion formulas that you'll need to know when we're trying to convert polar to rectangular or rectangular to polar. X is equal to r cosine theta. So if you know the radius and if you know a point r theta, then again we can calculate what the x coordinate would be in rectangular. Y is going to be equal to r sine theta. Tangent of theta is equal to y over x. So if you have your rectangular point, you can convert to solve for theta by taking the y coordinate dividing by x. R squared is equal to x squared plus y squared. So these are the conversion formulas you're certainly going to need to know when we're dealing with this particular section involving our polar. So for example, a point P has the polar coordinates 3 pi over 6. Find its rectangular. So now remember, we're given an r and a theta value. What we want to calculate is a point in rectangular. It means we need an x and a y coordinate. So we have our conversion formulas. I know that x is equal to r cosine theta. Y is equal to r sine theta. So I have an r value of 3. I have a theta value of pi over 6. So to calculate the x coordinate, it's going to be 3 times the cosine of pi over 6. So that's going to be 3 times square root of 3 over 2. This cosine of pi over 6 is square root of 3 over 2. Y is going to be equal to r sine theta. So 3 times the sine of pi over 6. So 3 times 1/2 will give me 3 halves. So the rectangular coordinate then is going to be 3 square root 3 over 2, 3 halves. Now the one thing about polar, if you remember, points are not unique in polar. In other words, we know a point in rectangular, there's only one way to describe that location of a point. In polar, because of all the different theta values, and when you have a negative r value with a reflection across the origin, there's an infinite number of ways we can describe a location of a point in polar. So for example, a point P has a rectangular coordinate of 4, negative 4. Find 4 sets of polar coordinates that satisfy the given conditions. Again, I've got an x and I've got a y. My x is 4, negative 4. What I want to convert to is an r theta. So this first example is when r is greater than 0 and theta is between 0 and 2 pi. We call this, by the way, primary representation. And most of the time you're going to see your points given in primary representation. So to find your r value, remember you have the conversion formula, r squared is equal to x squared plus y squared. So r squared is equal to 4 squared plus negative 4 squared. So that's going to give me r squared is equal to 32. And to solve for r, I can take the square root. So r is going to be equal to 4 square root 2. Theta, I have the formula tangent of theta is equal to y over x. So what I have to do then is take the inverse tangent of the absolute value of y over x. So I'm going to take negative 4 and divide it by 4. So this is asking me for the inverse tangent of 1. Now the reason why you're going to do the absolute value, this is going to be your reference angle. Remember from pre-calc, your reference angle is always the distance between your x-axis and the terminal side of the angle. And remember, reference angles are always positive and less than 90 degrees. Because of the different representations we can come up with, we are going to use pi over 4 as our reference angle, which may or may not be answering the theta value that we want in this particular description. So I want r to be greater than 0 and theta to be between 0 and 2 pi. Now the one thing you want to make sure of is look at the location of the ordered pair that you are asked to convert to polar. We know that 4, -4 is located down here in quadrant 4. So when you find your theta value, again, in polar, we're expressing an r and a theta value. You need to make sure that that theta value is actually an angle down here in quadrant 4, because that's where this point that we're trying to convert is located. Pi over 4 is an angle up here in quadrant 1. So then the theta value that I'm going to use to express this point in polar is going to be my r value of 4 square root 2. But again, my reference angle is pi over 4, so I know that it's going to have to be 7 pi over 4 down there in quadrant 4. So now take a look at this one. I want to, again, still using 4, -4, but now I want to express it where I have a positive r value, so I know it's going to be 4 square root 2. But my theta value I want to be between -2 pi and 0. Remember, a negative angle measurement is going to go in a clockwise rotation. So then I know that it's going to have to be -pi over 4 is the theta value to give me that point located down here in quadrant 4. Now, with negative r values, a negative r value is actually going to take a point and it reflects it across the origin. So if I have a point down here in quadrant 4 and I want to express with a negative r value, I've got to pick an angle up here in quadrant 2. So again, negative r values do a reflection across the origin. So for example, I have -4 square root 2. So again, what happens is this point I want to be down here in quadrant 4 now shoots up here into quadrant 2. So the angle measurement I'm going to have to use for theta, the angle measurement up here in quadrant 2 with a reference angle of pi over 4 is going to be 3 pi over 4. Because at 3 pi over 4, that would put me in quadrant 2, but with a negative r value, that will reflect me down into quadrant 4, which is where my point is located. So again, r is less than 0, and I have an angle from -pi to pi. So again, I know it's going to be -4 square root 2. And again, like I said, an angle measurement between -pi and pi would be 3 pi over 4. But there's an infinite number of ways you can describe a location of a point in polar. So sometimes now, instead of converting points, we're going to convert equations. So again, we've got 2x squared plus 3y squared in polar coordinates. When they say polar coordinates, that means they want to express it in terms of r and theta, not as an actual point. So we know, remember, that x is equal to r cosine theta, y is equal to r sine theta. So what we want to do is we want to replace x with an r cosine theta, y with an r sine theta. So I can rewrite this as equation as 2 times r cosine theta squared plus 3 times r sine theta squared is equal to 4. Now remember, when you square this quantity, you square the coefficient as well as the cosine. That's going to be 2r squared cosine squared theta plus 3r squared sine squared theta is equal to 4. So when you're doing these conversions, when you want to convert an equation into polar, typically what you want to do is you want to solve for r or r squared, or if it's a really difficult equation, you simply just set one side equal to 0. But typically when you're writing equations in polar, we solve for r or r squared, or we set the equation equal to 0. So notice I can factor an r squared out of the left-hand side of this equation. So I have r squared times 2 cosine squared theta plus 3 sine squared theta is equal to 4. And now I can solve for r squared by dividing. So r squared is going to be equal to 4 divided by 2 cosine squared theta plus 3 sine squared theta. So now on the next page, I also gave some information regarding special polar graphs, but there's some common curves in both polar and rectangular. So what we're just going to do is we're going to convert these polar equations into rectangular equations to see what kind of shape we would actually be sketching. So again, I know that r squared is equal to x squared plus y squared, so r is going to be equal to the square root of x squared plus y squared. So then I can take the square root of x squared plus y squared and substitute 3 in for r. So now to solve this equation for x squared and y squared, I can square both sides of this equation. So I end up with x squared plus y squared is equal to 9. And if you remember from rectangular, this is the equation of a circle. The center of this circle is at 0, 0, and the radius is 3. Again, looking at b, r cosine theta is equivalent to x. So in rectangular, this is what the equation would be, x equals 5. R cosine theta, this is the equation of a vertical line, intersecting your x-axis at 5. So r is equal to negative 4 cosecant of theta. Well, again, I have conversion formulas involving r sine theta and r cosine theta. So I'm going to change cosecant. Remember, cosecant of theta is equal to 1 over sine theta. So r is equal to negative 4 over sine theta. I can multiply both sides of this equation by sine. So I have r sine theta is equal to negative 4. And again, there's that conversion formula, r sine theta, that I can substitute. R sine theta is equal to y. So y is equal to negative 4. So there's my equivalent rectangular equation. Again, this is just a horizontal line. So now, looking here, I have r is equal to secant theta times tangent theta. Again, change this in terms of sine and cosine. So I know secant is equal to 1 over cosine theta. Tangent is equal to sine theta over cosine theta. So then when I simplify this, I know that r is equal to sine theta over cosine squared theta. So now it would be really helpful if I had an r in front of both sides of this. So what I'm going to do, again, first of all, I'm going to multiply both sides by cosine squared theta. So r cosine squared theta is equal to sine theta. I'm going to multiply both sides of this equation by an r, because really to get rid of this sine theta, I'm going to need an r in front of it. So I have r squared cosine squared theta is equal to r sine theta. Another way I can write r squared cosine squared theta is the quantity r cosine theta to the second power is equal to r sine theta. So now I can replace r cosine theta with x, so x squared is equal to y. So that's your equation of a parabola. So the theorems about in polar, there is symmetry in these polar curves. A curve in polar coordinates is symmetric about the x-axis if we're replacing theta by negative theta in the equation. A curve in polar coordinates is symmetric about the y-axis by replacing theta with pi minus theta. It's symmetric about the origin if replacing theta by theta plus pi, or by replacing r with negative r. So again, you can kind of see what those symmetry are by these particular graphs. So let's take a look at some common polar graphs or special polar graphs that you guys studied last year. So first of all, you have your limazons. Limazons may have an inner loop, or we call this a dimpered limazon or a limazon without an inner loop. A cardioid is also a special type of limazon. So now how do you know you have the cardioid? A cardioid, these are your common equations. Again, it's going to be the relationship between A and B. So a limazon equation is r is equal to A plus or minus B cosine theta. The cardioid will always have the indentation at the pole, and this is going to happen when your A and B are the same number in this particular equation. If the A is less than B, you will have the limazon without the inner loop. And notice this indentation is not at the pole. And then the limazon with the inner loop is B is greater than A. You also have your roses. whatever the coefficient is, that's how the number of petals you're going to have. It'll have double the number of petals if the coefficient in front of your theta is larger. So again, here's your standard form of what your Rose equations are going to look like. It could be in terms of sine or cosine. Again, so you can look at this coefficient n and decide how many petals there are. If n is an odd number, it's equal to the number of petals. If it's an even number, it'll double. You also have circles and lemniscates. Again, here is your equation of a circle. R could be equal to a sine theta, or a is equal to cosine theta. Again, cosine curves in polar will always be symmetrical to the polar axis. So any shape that we're graphing, if it's a cosine in the equation, it's symmetry with respect to the polar axis. Sines are symmetrical with the line theta equals pi over 2, or what you think of in rectangular as the y-axis. We don't have a special name for the line theta equals pi over 2 for the y-axis. Polar axis, remember, is what you think of as the x-axis. So let's take a look at some examples. So here we have r is equal to 5 minus 5 sine theta. So again, because a, here's your a, here's your b. So since a is equal to b, we have a cardioid. So that's that heart shape. The symmetry, because it's a sine, is with the line theta is equal to pi over 2. So now the quickest way to graph your cardioid, again, these are just going to be sketches. They don't have to be exact. So look at your A and B values. So that's going to be your distance from the center, or from the pole. So now, because it's a sine, I know I'm going to have symmetry with respect to the line theta equals pi over 2. Because this is minus, a majority of the limison is going to have to be on the negative side of your line theta equals pi over 2. And then if I add those A and B values together, that's going to give me the distance, this point on the line theta equals pi over 2. So it's going to be a heart shape. Come up. So you can find your intercepts of the polar axis as well as the line theta equals pi over 2. Because again, I know that the sine of 0 is going to be 0, so that's where I get this point from. The sine of pi is 0, so that's going to give me another 5. Again, this isn't really negative 5 over here. Remember, we're talking about the distance from the origin because we're graphing in polar. And then again, I know the sine of 3 pi over 2 is going to be negative 1, so that gives me that 5 plus 5. So here's another graph. 1 plus 3 cosine theta. Again, A is less than B. So I have a limison with a loop. And because it's a cosine, the symmetry is with the polar axis. So now if I add A plus B, that's going to give me 4. So 1 plus 3 is equal to 4. If I subtract the difference, that gives me 2. This is the length of the outer part of the loop. This is the length of the inner loop. Now, because this is positive, a majority of this limison is going to be on the positive side of the axis. Again, I've got symmetry through the polar axis. So again, when I add them together, that 1 plus 3 is 4. So that's the outer part of the loop. The inner loop is going to be 2. Now, if you think about the intercepts for the line theta equals pi over 2, you can plug pi over 2 in for theta. When I plug pi over 2 in here, I know the cosine of pi over 2 is 0, so that's going to give me that 0.01. So there's my theta, there's my r value. Again, since I have symmetry with respect to the polar axis, this point up here at pi over 2, 1 is going to have to reflect down here. So again, I can sketch my inner loop starting at the origin. I'm going to come around, form that inner loop. It's going to come around, hit that line theta equals pi over 2, come down, come back up, and then intersect the pole again. So you can build a table of values to help you sketch the graph as well. So now this is a case where A is larger than B. So this is a limazon with no loop. It's a sine, so I know I have symmetry with respect to theta equals pi over 2. Because this is positive, a majority of this graph is going to be above the polar axis. It's going to be on the positive side of the axis. So again, I can add 5 plus 3, which is 8. So that's the distance from the pole to the outer part of the limazon. And if I subtract, that's the distance from the pole to the outer part, the other distance from this pole to the outer part of the limazon. Again, I can find my x-intercepts again, or I can find my intercepts with the polar axis. Again, this is where sine is going to be equal to 0. So when sine is 0, that's going to give me 5. At pi will give me the other intercept with the axis. Again, that's going to give me 0. Again, that's going to give me 5. So I can draw my limazon without the loop. It looks a lot like a flattened circle on this one end. Some limazons, the indentation is much more defined. So again, this is going to be another cardioid because A is equal to B. The symmetry is with the polar axis. Again, because this is minus, the majority of this limazon is going to be on the negative side of the polar axis. So same thing, you can always build a t-chart, picking some theta values. You really want to find the intercepts with the polar axis and the line theta equals pi over 2. So again, it's going to intersect my polar axis. Again, if I plug in 0 for theta, well, cosine of 0 is 1, 2 minus 2 is 0. So that gives me a point at the pole. Another intersection point at the polar axis will be at pi. Well, I know cosine of pi is negative 1, so 2 plus 2 is going to give me 4. Which notice, had I add 2 plus 2 together, which I did in the first example, is where I got the 4 from. The intersection points on the line theta equals pi over 2 is going to come from when cosine is equal to pi over 2. Well, I know cosine of pi over 2 is 0, and 2 minus 0 is 2. And again, I've got symmetry over the polar axis, so at this point I can also reflect down here. And there's my heart-shaped. Remember, the cardioids will always have that indentation at the pole. So now, the roses is when you have a coefficient in front of theta. So because this number is odd, it's equal to the number of petals. So I know this is going to be a rose with 3 petals. Now the coefficient is significant because that tells you what the length of each petal is. Now you also want to know the spacing between the petals, so we can find the tip of one petal. You find the spacing by taking 2 pi and dividing it by the number of petals. So the spacing between each petal is going to be 2 pi over 3. All you need to do is find the tip of one petal, and then you can find out where the other petals are going to be located. If it is a cosine rose, you will always have a petal point on the polar axis. Because, for example, if I plug in 0 in for cosine, I know the cosine of 0 is 1, and 1 times 4 is 4. So the tip of my one petal, because again, I know the length is going to be 4, the tip of my first petal has to be on the polar axis at 0, 4. So there's my one petal. The tip of my next petal has to be 2 pi over 3 units away from that. So 2 pi over 3 is located up here in quadrant 2. And again, had I had an exactly, you would see a graph that looked like this. You would count out 4 units. So there's the tip of my next petal. The tip of my next petal is going to be 2 pi over 3 units away from that. Well, 2 pi over 3 plus another 2 pi over 3 is going to put me down here at 4 pi over 3. So there's the tip of my third and final petal. So there's my rose with 3 petals. 5 sine 2 theta. So since this number is even, I have to double for the number of petals. So the number of petals is equal to 4. The length of each petal is the coefficient, which is 5. The spacing is going to be 2 pi divided by the number of petals, which is 4, which is going to be pi over 2. And again, if it's a sine, there's going to be no petal on the polar axis. So since I have 4 petals and they're each placed pi over 2 units apart, the tip of my first petal, 1, 2, 3, 4, 5, is going to be at pi over 4. So there's my first petal. Another pi over 2 units away is going to put me over here in quadrant 2 at 3 pi over 4. And then down here in quadrant 3 would be at 5 pi over 4. And then in quadrant 4 it would be at 7 pi over 4. So that's how you graph the special curves, polar curves.